Hey guys, welcome. Today we're going to be taking a look at the minimum window substring question on Leetcode. Now this question consists of taking two strings, one called S and one called T, and trying to find the minimum window in S, the minimum substring in S that contains all of the letters in T. And if we can't find any such window, any such substring that contains all of the letters in T, we're just going to return an empty string. The one interesting point that's highlighted in bold here is that the T can include duplicates. So if there are multiple repeating characters inside T, we have to find the same number of characters in S before we can consider it a valid window. Now let's take a look at a couple of examples. What I would like to mention before we do that is that this is a perfect candidate for the sliding window technique. Which I'll get into in a bit, but essentially if we're trying to look at the input set and we're trying to optimize a sub-range in the input set, just like we are with S, we're trying to optimize a sub-range in S, then the sliding window technique might be something that could be helpful. And what we're going to do first, however, is just take a look at a couple of examples. So here we have S is equal to A, B, 1, 2, 3, and C, and we have T equal to 1, 2, 3. Now this one is pretty straightforward. We can see that T can be found in S right here. As it looks like in T, it's found directly in S. Same order, plopped right in the middle. But we should also note that there are other substrings that contain all of the letters in T, but some other characters, for example, B123, B123C, you get the idea. There are more than a few substrings that contain all of the letters in T within S. But what's so special about that first one that we highlighted is that it's the smallest one. And there can't be a smaller one than that, because that is the number of the characters that are in T are 3. We can't get smaller than that without losing one. So that's what we're looking for. We're looking for the smallest that we can possibly make it, substring in S that contains all of the letters in T. Taking a look at a bit more complicated of an example, we have 1, 2, 3, again, ST, and then S is a bit more complicated. It has A1, B2, C3, D1, 2. And you can see that 1, 2, 3 is spread out in a couple of different variations inside S. But we can still spot sort of pretty easily that there's a 1, 2, 3 here, right? And now there's actually another one here, 2, 3, 1. Remember, it doesn't have to be in the exact same order that it shows up in T for it to be valid. Are there any other? Oh, there's one more. There's 3, 1, 2 here. Now there are other substrings in S that contain all of the letters in T, but they're bigger than the ones that I've highlighted here, so I won't look at those. And out of the ones that I've highlighted, the purple one is the smallest, 3D12 with 4 characters, and then the other two both have 5 characters. So this might give you a clearer picture of what we're looking for, maybe some of the complexities in the problem, where T can be found in a different order, spanned across other characters that aren't in T, and there can be a couple of different variations of it that are found. And out of all of the ones that we find, we're looking for the one that is the minimum. Now let's take a look at a final example here. Say T is 1, 2, 3, 4, and S is A, B, 1, 2, 3, C, D, E, F. Now we can see that there's a 4 in T, but there's no 4 in S. And so right away we know that this pattern T can never be found in S. And so here we would just return an empty string. Alright, so out of the examples that we saw, let's try to come up with a brute force approach that gets us close to an efficient algorithm. And we can always start with brute force and optimize later. This is a well-tested, battle-tested strategy for programming interviews. If an efficient solution isn't immediately clear to you, always think about what could be the brute force approach. So what is the brute force approach that returns us the minimum window substring in S that has all of the letters in T? Namely, in this example, it would return 3D12, and in the example above, it would return 1, 2, 3. So take a minute, pause the video, try to come up with an algorithm, a series of steps, maybe some code or thoughts of a brute force approach. It doesn't have to be optimized, but a brute force approach that returns us the minimum window substring in S that contains all of the letters in T. All right, welcome back. Now let's think about what the problem is asking. So the problem is asking us for the minimum window substring. It's asking for a substring in S. So our solution is one of the substrings of S. A truly brute force approach would be to generate all of the substrings of S and narrow it down, filter those until we get our solution, the one that fits our criteria of being the minimum window substring of S that contains all of the letters of a T. How would that look like? Let's take a look at an example where S is equal to AB 1, 2, 3, C, and T is equal to 1, 2, 3. So if we generate all of the substrings of AB 1, 2, 3, C, it would look a little something like this. And out of these substrings, we want to narrow it down so we identify the minimum window substring of S that contains all of the letters in T. So first off, let's just identify the ones that have all of the letters in T in S in these substrings. So the ones that have 1, 2, 3 within them. Just go ahead and mark them with a thumbs up. And the rest do not. So out of the ones that we marked with a thumbs up, we only want one, and that is the one that is at the minimum. And so we can see that this is the minimum one here, 1, 2, 3. So that is the brute force approach, where we generate all of the possible solutions, all the possible substrings. And out of those substrings, we try to narrow down until we get one solution that fits and matches our criteria. So this works, but it's quite inefficient. We'll get into why in a bit. Let's come up with a time complexity here. The time complexity is dominated by the search for substrings, the computation of substrings of S. And say the length of S is n, then it would be O of n squared. And this is because the computation of substrings takes about the sum of 1 to n, the natural sum. That's how long it takes to compute the number of all of the substrings of a given string. And that gives us a big O, worst case time complexity of O of n squared. Why is this inefficient? What is the brute force approach doing that is overcomputing? Well, it's searching substrings that could never be a valid substring. It could never be the minimum window substring. For example, here we see that it continues generating substrings after it sees that AB12 is a substring, and then it goes AB1, AB, A, and then A. But it should have stopped at AB12 because any substring of AB12 will never be valid. It can never contain something it doesn't already have. It can't find that 3. So that'll never be valid. So what we want to do is look through the substrings, the windows in S, in a way that we're not overcomputing. We're not computing substrings. We're not computing windows that could never be valid. And this is where the sliding window approach comes in. All right, so the sliding window technique is useful when we have a question that's asking for an optimal subrange in the input set. In this question, the input set we have is S, and we're looking for the optimal subrange, as in the minimum window substring that matches our constraint of having all of the letters in T. So the sliding window technique is a good candidate for a template problem-solving technique here. What it'll involve is we'll keep track of a window using a left and a right pointer, a left pointer pointing to the beginning of the window and a right pointer pointing to the end of the window. We'll go through an example to work it all out. So let's say S is A1, B2, C3, D1, 2, and T is 1, 2, 3. Then let's create a window on it. And let's say that initially the window is initialized where both the left and the right pointer are pointing at the same thing, the same element, which is the first element, A. What we want to do is we want to expand the right pointer up by 1 until this window contains all of the letters from T, until this window is valid according to our constraints. So Previously it was a, now it's a1. We've expanded the right pointer up by 1. We're going to do that again because it's still not valid, so we have a1b. And again, once more, because it's still not valid, a1, b2, and so on, until the window becomes valid. And that'll happen here. So we have a1, b2, c3. We've expanded the right pointer until the window has become valid. And when we get to a valid window, every time we want to check the length of it to see if it is below our candidate for the minimum window. So the length of this is 6, and this is the minimum that we've seen so far. So we'll record that. And as you can see here in the next step, we contract the window. So when we have an invalid window, we expand the window by moving the right pointer up by 1, but once we have a valid window, we contract it by moving the left pointer up by 1, and so the window becomes smaller. And the reason we do that is so we can find the minimum window. We keep contracting the left pointer, and we keep moving the left pointer up by 1 and contracting the window until the window no longer is valid according to our constraint, until it no longer has all of the letters from T contained within it. It doesn't have 1, 2, 3. So if we move the left pointer up by 1 initially, it's still valid, and since it's valid, we record the length of the valid window. It's 5. It's less than our current one, so this becomes our new candidate for the minimum window substring that contains all the letters from T. And we contract one more time, moving the left pointer up by 1, and we can see that it's not valid anymore. It doesn't have a 1 in it anymore, and so it doesn't have all of the letters from T within it. What does that mean for us in our algorithm? Using the sliding window technique, we expand the window. Expanding the window means moving the right pointer up by 1. So we do that. Now it contains D. It's still not valid because it's still missing that 1. And if we move it to the right one more time, we can see that it has now become valid. And so we record the length, it's 6. And since it's a valid window, we contract it by moving the left pointer up by 1. And so the left pointer moves up by 1. And we get another valid window. This window has 5 as the length. It's the same size as the last minimum candidate, so it doesn't really help us. We continue by contracting the window one more time by moving the left pointer up by 1, and we can see that it no longer is valid. It doesn't have 2 within it. It's missing the 2. So since it's invalid, we'll expand the right pointer up by 1. When the right pointer is expanded by 1, we see that it has become valid. It contains all the letters from T, 3D, 1, 2. We record the length here. It's 4. Oh, this is our new minimum. So our new minimum window. And since it's valid, we want to contract the window by moving the left pointer up by 1. Moving that up, it no longer is valid, and we are done at this point because we can't move the right pointer up by 1, and moving the left pointer up by 1 would decrease the window size so that it is smaller than our desired length. Therefore, we can exit the algorithm and look at our candidates and pick the minimum one, which is 4. And so the minimum candidate, the minimum window substring is 3D12, and that's what we return using the sliding window technique. So, hey guys, let's get into the coding portion of this algorithm that we just saw. And initially what we want to do is just break out the cases where S is empty or T is empty, so we get that out of the way and we only have to deal with the non-empty cases. What happens if S is empty, not S in Python? Well, then we won't be able to find any pattern T within it. So we would return empty in that case. But we'd also return empty when T is empty, because then by default we find it in any S. So we'd always return the empty string when either S or T are empty. So that gets the empty cases out of the way. Now we can move on to the actual sliding window technique. And for that, we have to define a couple of variables. First of them being frequency of T, freq T. And freq T will use the counter class in Python to generate an object that has the unique characters of T mapped to the frequency of their occurrences. So if there are 3 characters, for example, 3 A's in T, then this object would be A mapped to 3, and so on and so forth for all of the other unique characters. Another variable that we'd like to keep track of that'll help us implement the sliding window algorithm will be the frequency of the characters in window. long name, but this it also tracks frequency of characters, but it's only the frequency of the characters that are in our window. And this will be an ongoing count that will subtract and add to when the window increases in size and contracts in size. Remember, the sliding window technique has a left and right pointer that keeps track of a window that we use essentially to search the input string and find our optimal set, our answer, the minimum window substring. And in order to do that, in order to find the answer, we need to keep track of another variable, and this one will be called num_missing, and this will be equal to the frequency of the characters of t. The num missing is the number of characters that we currently are missing from our window for, and when num missing is 0, we are missing 0 characters from our current window, and so our window is valid. So the importance of this variable is that it helps us keep track of whether or not we have a valid window. Okay, moving on. Another variable that we'd like to keep track of is obviously our answer variable. Our answer variable will be a tuple. It'll hold 2 values, one being the left. So you can say initially this is negative infinity, and the right, which is positive infinity. Left, right of minimum window substring s. And we'll return s at answer 0 to answer 1. And that's only if we're able to find a minimum window. So if answer is negative infinity or infinity for any one of those 2 values, then we'd actually we haven't found a valid window at all. So we'd return empty in that case. And in order to do that, we'll just do a check above if answer at 0 equals cool. So now we have all of the variables defined to run sliding window. And the main bits of sliding window rely on 2 pointers, a left pointer that will initialize to 0, and a right pointer that will actually use a for loop to increment. And it'll start at 0 and go to the length of s. We'll keep track of a variable called character that is equal to what's inside s at right. And we also want to update this frequency of characters that is in our current window. So characters in our current window, we want to update the frequency of character by 1. And to do that, we can just do frequency.get character and give it a default value of 0 and add 1. What this allows us to do is to check, well, we first check if the character is interesting to us, and if it's interesting if it occurs in t. So if character is in frequency of t, then we want to do another check on it. We want to check if we've encountered this character the number of times that it occurs in t. If we've encountered this character in our current window, if we've encountered this character the amount of times that it occurs in t, then then we don't have to look for this character anymore. Then we can decrement that num missing variable by 1 because we have 1 less character to look for. Remember, that starts at the number of unique characters in t, and when that reaches 0, that means that we have found the required number of characters for all of the unique characters in t when num missing is 0, and that means we have a valid window. So that's why that variable is important, and that's why we have these other variables that are keeping track of the frequencies, occurrences in our current window, and their total occurrences. So if the frequency of the characters in the current window, if the frequency of the character in the current window is equal to the frequency that occurs in t, then we can decrement num missing by 1. And while num missing is 0, so if the window is valid, that's while num missing is 0, and left is still less than or equal to right, because we're going to want to increment left here, because we're contracting. So since the window is valid, we want to contract the window, but before we contract the window, we're going to need to check if the current valid window is less in length than the window that we have in our answer variable. So our answer variable, so if say right subtract left is less than answer at 1, subtract answer at 0, then we can say answer is equal to left, right. If the length of the current valid window is less than the answer that we've been keeping track of so far, and initially any length of any valid window will be greater, it would be less, then we want to update our answer. And after we've updated our answer, we want to contract the window and see if we still have a valid window. If num missing is still 0, and then if we do, we keep on doing that until we've minimized the current window. And so we get the minimum version of this valid window to check our answer against until the window is no longer valid, at which point we'll continue looking for a valid window. So we have another character that is we're going to check if it's interesting to us. It's character at left currently, so we'll check s at left. And if first we want to decrement the frequency of the occurrences of this character by 1. And then we want to check again if this character is interesting to us. It's interesting if it occurs in t, great. And if the frequency of occurrences of this character is less than the number of times that it occurs in t, then we want to add 1 to num missing, because now we have less than the number of required characters. For this particular character, we have less than the number we need for us to encompass all of the occurrences that it has in t. And so our num missing variable goes up by 1. It is no longer a valid window. And we also move left up by 1. And that's it. So this covers all of our cases. Let's try hitting submit. Boom. We have an accepted answer. Thank you for watching, guys. Hit like and subscribe if you learned anything from the material. Please give a comment if you have any feedback. Thanks, and have a wonderful day.